Hello and welcome to this video on chemical thermodynamics. In this video, or by the end of this video, you should be able to recognize that the method that we use to calculate delta H and delta S is pretty much the same as calculating delta U. And that to calculate delta H and delta S, we can do that using an ideal gas heat capacity and an equation of state, like delta U. Now, if we're wanting to use the method that we used in the previous lectures on calculating delta U with the equation of state, then what we need is similar equations for enthalpy rather than just internal energy. So what we do is we just start with the definition of enthalpy, and then we define the departure enthalpy in terms of internal energy and then also the PV contribution as well. And so from earlier on, we've already got an equation here for the internal energy departure function. So now we need something for the PV term. And so the PV departure is simply the pressure times by the volume minus the pressure times by the volume that an ideal gas would be at that temperature and pressure. Now the ideal gas law, of course, says that PV is equal to RT, and for a real gas we can write that PV is equal to Z RT, okay, where Z's the compressibility. So if we substitute these two equations into here, then what we get is that this is equal to ZT minus RT. So taking RT outside, then we're left with Z minus 1. Okay, so then we substitute that into the equation, and what we're left with is that the H departure is equal to this PV departure term that we just derived, plus the term here for U departure, which we've already looked at and worked with. Okay, and again, just to emphasize the point that this term here is the partial differential of the equation of state, and importantly, this term here is the equation of state. Okay, it's not just a fixed number; it's an equation. Okay, so now this gives us an equation to be able to calculate the H departure, which is good because this is what we're using in virtually all of our energy balances. Now, if I'm wanting to calculate delta H, then I'm looking at calculating delta H here between two states. Okay, so between T2 and P2 and T1 and P1. Then what I can do is express this in terms of the ideal gas heat capacity and departure, and then of course I can do that for state 1 as well, so ideal gas and departure. And so then grouping these terms together, so my delta H is delta H of the ideal gas part, and then the departure enthalpy at state 2 and at state 1. And so expanding on each of these terms then, so my ideal gas contribution is just the integral of the ideal gas heat capacity. And then my departure at temperature 2 and pressure 2, I'm just filling in these terms. Okay, so temperature 2, the compressibility at state 2, temperature 2 as well here, and then I'm filling in my partial differential and my equation of state. Okay, and then of course at state 1 we've got temperature 1 and compressibility at state 1, temperature 1, and then we're integrating from infinity to V1, and then at state 2 from infinity to V2. Okay, so this is identical to what we were doing for internal energy. We've just added this term here at the front. Okay, you can think of this in terms of a path. So if we're going from state 1 to state 2, okay, so I've got my real path here, whatever the process is that's happening. But then to get from state 1 to state 2, I could construct a path where I go from my pressure that I'm interested in at a fixed temperature to pressure equal to 0, which is the ideal gas state, change the temperature, okay, because enthalpy is only a function of temperature for an ideal gas, and then change the pressure again. And so then step 1, so this first step here, is just the negative of H departure, okay, because we're going from real to ideal. Step 2 is just the integral of the heat capacity for the ideal gas, and then step 3 is H departure, and because we're going from ideal gas to real, then it's the actual departure function. Okay, so you might find that helpful to think about it that way. Now for changes in entropy, so what we'll do first is we'll go through the approach like we did with internal energy. So the first thing we can do is say, okay, well the absolute differential of the entropy is ds to t, and then ds to v. Now that I've got these terms, then like these aren't particularly useful for calculating anything, so I'm going to start using some properties and relationships and Maxwell relations to be able to get something useful. The first thing is that I can replace this term by using a Maxwell equation, a Maxwell relationship, and so that gives me a p to t term. Okay, and so this is something that obviously I can calculate from an equation of state. The term that we've got left here, okay, I can expand this out, and that gives me these two partial differentials. Okay, and so the first partial differential here, so I have a thermodynamic identity here, and so this one up here, okay, is just 1 on T. Okay, it's just the inverse of this relationship. And then du to T is just equal to heat capacity. Okay, so that's that term there. So when you combine these two things, not add them, when you multiply those two things, then you end up with CV on T. Okay, so substituting these back into the equations above, okay, so substituting this term, then we end up with the equation for ds. And so then we can integrate this, and we end up with an equation for delta S. Okay, and so we've already used this equation in calculating changes of entropy for an ideal gas. Now, if we're going to calculate departure entropy from an equation of state, we need to be a little bit careful here. Okay, and that's because the ideal gas entropy is a function of temperature and pressure. So I can already see that I've got a slight mistake in the slide here. So this here should be T comma P. Okay, so because the ideal gas entropy is a function of temperature and pressure, and so rearranging just the definition so I can get the S departure. Now for the real gas then, I can say, well, my entropy is equal to my ideal gas entropy at this extreme of P equal to 0 plus the integral from the previous slide. So if we go back to the previous slide, we're going to be using the this part of the integral here. Okay, so at a fixed temperature, I'm integrating from high volume. Okay, so from my ideal gas to the volume that I'm interested in. Then for an ideal gas, okay, I can do a similar thing. So the ideal gas entropy is the entropy at very low pressure plus the integral from high volume to the volume that I'm interested in, and this one here should be the ideal gas entropy. Okay, so and we get this from the fact that for an ideal gas, P is equal to RT on V, and so then to P to T is equal to R on V. So that's the partial differential at fixed volume. Okay, so So this is just substituted into here, and so then we get an equation for, okay, what's the entropy of an ideal gas as I change pressure, and we've dealt with this in previous problem sets. Now if I take this equation away from this equation, the two terms at low pressure or zero pressure cancel each other out, and then I'm just left with the terms in the integral. And so what I end up with is a final equation here for calculating the departure entropy, okay, where we've got the contribution from the equation of state minus the change in entropy due to the ideal gas. Okay, so, and now we can use this equation in exactly the same way as what we've used for internal energy, where we have an ideal gas contribution and then a departure contribution if I'm wanting to calculate changes in S. And so we can see that here in on this slide, where so we start at the difference between state 2 and state 1. Okay, we can break that out into the ideal gas and departure contribution, and again the ideal gas and departure contribution for each state. We group the ideal gas contribution together, okay, and so then we can calculate that using the equations that we've used in the previous section, and then the departure parts we calculate using the equations that we've just derived. Okay, so this is for state 2, this is for state 1. Okay, and so you can see that we have to integrate between infinite volume and the volume that we're interested in for that state. Okay, you always have to remember to update that.
Now this has been a whole lot of equations, and unfortunately that can't be avoided. But there are a couple of key points here. One key point is that all thermodynamic quantities are interlinked. So if we have pressure and we have that as a function of temperature and volume, that then means that we can calculate all these other things, or changes in all these other things, by using that equation that relates these three properties. Similarly then, if you combine any other three things, you could then relate one of these to everything else here. And so what we get is a really interconnected web. And so all it takes is some time and some imaginations to be able to link all these things together. Okay, I'm not going to ask you to be linking extra stuff. It's just to know where these things come from. And that the equations that we use to calculate the change in different properties. Okay, so if we're interested in the change in U, the change in S, the change in enthalpy, and then later on we'll be interested in the change of Gibbs free energy, we can derive these by using our fundamental equations and using partial derivatives. That then allows us to use this property group to then calculate these changes. And so from all this, it means that you can calculate the change in any property as long as you have the ideal gas heat capacity and you have an equation of state. So to recap, we can derive the equations for dH and ds using similar techniques as we used for du. A three-step path is used to calculate changes in these variables, just as we did for the internal energy. And also, not written here, but we also have a choice of the equations that we use for du, dH, and ds, depending on whether our equation of state is pressure equals something, 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 or whether our equation of state is volume equals something, something, something. Okay, thanks a lot for your time.